transactions while preserving its security. For instance, I can take a transaction, transaction 1, another transaction, transaction 2, and mix them together into a new transaction that contains the information from both. And this is the second thing that's very peculiar of Mimblewimble. If an output is being spent as a new input in transaction 2, then these entries in both transactions can be removed once the transaction is merged. So we can really remove information that is not necessary for holding the information. This is the cut-through thing that I was mentioning before. And this is really peculiar. We don't have anything like this in other cryptocurrencies. However, one of the problems with Mimblewimble is that despite its aggregation is non-interactive, both parties, sender and recipient, need to be online when we make a simple transaction. There is no concept of address or wallet to send money to. And this is also very different from other cryptocurrencies, and it's the first problem that we tackle. The second problem is that some metadata information in transactions that we call the excess, that essentially says the transaction is balanced. The sum of the outputs minus the sum of the inputs. Well, when we merge transactions together, this excess holds information about the composing transactions and it leaks information about them. This is the second problem that we tackle in terms of adding privacy on the top of Mimblewimble. More specifically, we give two new security definitions. One of them is transaction binding, which covers something that was not really thought of in the first model in our work of Asiacrypt 2019. What happens to a transaction before it goes to the ledger? With transaction binding, we say essentially that once a transaction is broadcasted, only the intended recipient can spend an output that was honestly generated. This protects, for example, against malicious miners that might try to tamper with transactions before they reach the ledger and are in the mempools. Or for instance, against adversaries, they might change their mind about the transaction that they sent, and they might want to spend the output before the honest recipient will. Additionally, we introduced this new notion of transaction privacy, where essentially we say that from a transaction, you cannot learn anything about the transaction amount. So the values are hidden, the recipient addresses, or which inputs and outputs belong to the same constituent transaction once aggregated with another transaction. In order to do so, we use two key ideas. One of them is stealth addresses, and the second one is transaction offsets. Stealth addresses are key for non-interactive transactions. They work roughly as follows. When Alice wants to send some money to Bob, it will use the public key of Bob to derive a new one-time public key. An observer cannot learn this cannot link this one-time public key to the public key of Bob. Now, Bob, on the other hand, has associated to the public key a secret key and a view key. From the view key, it is possible to regenerate the one-time public key. So Bob just has to scan the blockchain in order to find outputs that are destined to him using the view key. And using the secret key, it is possible to generate a one-time secret key that will be able to spend the output associated to the one-time public key. Now, transaction offset instead add privacy to this feature of Mimblewimble called non-interactive coin join, this aggregation. The idea is simply to add some random offset that I'm displaying here in yellow. And when we aggregate transaction, we will simply re-randomize this offset in such a way that no information about the component transaction is leaked. This feature was already available in green for a few years, but we provide the first study that guarantees its security properties in Mimblewimble. The resulting transactions in our new scheme look like the following pretty much. We have these one-time public keys that are introduced by stealth addresses, and we have signatures authorizing the spending under these public keys. Now, these signatures do not link input and output together as one would normally imagine in Bitcoin. Instead, we opt for something very similar to the access equations that we saw before, and we introduce a new access that depends on these public keys called stealth access. Now, the stealth access slightly weakens, unfortunately, another property of Mimblewimble called the cut-through. We, however, discuss in the paper trade-offs that can be made so that some sort of cut-through can still be achieved. We also have the offset that, just as we saw, provide privacy. And finally, as normal in Bitcoin, in Bitcoin's confidential transaction and in vanilla Mimblewimble, we don't have plaintext values that credit public key. Instead, we have commitments to those values together with range proofs that attest that these values are small and they don't wrap around the integer arithmetic. To conclude, in this work, we strengthen notions of security and anonymity that we provided in Europe in 2019, and we provide a new scheme that satisfies those and that supports non-interactive transactions. Our scheme is now in use both by Mimblewimble Coin and by Litecoin. Thank you.
Okay, thanks. Do we have any questions from the audience? Okay, looks like we don't have any questions, so we'll move to the next speaker, who's going to be talking about universally composable non-interactive aggregate cache. And that speaker is Yan Shui Jia, who hopefully is online.
Yeah, I'm online.
Okay, great. We can hear you, so you can take it away.
Okay, and can you see my slides?
Yes, we can see your slides.
Okay. Okay. I will start. Okay. Hello everyone. I'm Yan Shui Jia from Shanghai Jiao Tong University, and I will present our work, a universally composable non-interactive aggregate cache system. This is a joint work with Shifeng Sun, Hongsheng Zhou, and Dawu Hu. I'm breaking my presentation down into 4 parts, and because Michele has introduced the Mimblewimble, so here I just mentioned something related to our paper, and I will summarize our contributions and give more details about our scheme and the ideal functionality. Oh, I will skip this part. Okay. I will mention that the Mimblewimble has a beautiful feature called cut-through, and which means that if this coin is by this coin, then the 2 coins can be deleted in the aggregate transaction, and which is called cut-through, and it can save the on-chain storage cost. However, the Mimblewimble has a drawback, and it might entice the usage in practice. More specifically, the sender and the receiver must interact to generate a transaction, which means that the 2 parties have to be online at the same time. This is because in Mimblewimble, in each transaction, there must be a signature under the XSE. However, each party holds a part of the signing key. So our work aims to avoid the drawback of Mimblewimble. So we design a non-interactive aggregate cache system. We call it NIACS for short. And we formalize an ideal functionality for NIACS. And finally, we prove that our protocol can easily realize our ideal functionality in a hybrid model. In the original Mimblewimble, the essential reason why each party holds a part of the signing key is the sender cannot know the randomness of the output commitments because the randomness act as the spanning key of the output coins. And the XSE computed from the input commitments and output commitments. And the signature has 2 functions. The first is to prove that the transaction is balanced, and the second is to prove that the sender knows the spanning keys of the input coins. So the core idea of our work is to add the notion of address to achieve non-interaction, such that the secret key of address acts as the spanning key, and the sender can know the randomness of the output points. So the sender can generate the signature under XIS alone. And this signature just used to prove that the transaction is balanced. And the signature under the address is used to prove that the sender knows the spanning key of the input point. Given the initial idea of ending address to achieve non-interaction, there are also some challenges. First, how to bind a commitment and an address. Second, how to bind the proof of the ownership of the input coins with the transaction, and how to non-interactively transfer the private information of the output coins to the receiver. Finally, how to maintain the important feature pass-through. So let's first see how to bind a commitment and an address. Because the holder of the secret key of the address can span the coin, so we must guarantee that for each commitment, its address cannot be changed by others. In the privacy-preserving cryptocurrencies, the range proof is necessary. So in our work, we modify the range proof into a signature of knowledge. The signature of knowledge is a generalized notion of signature, where the verification key is a statement and the signing key is the witness. In our work, we use the commitment as the verification key and the randomness and value as the signing key. And the sender can use the signing key to sign on the address. In other words, the address is the message. So we can generate the signature of knowledge to bind the commitment and the address. The sender needs to prove that he knows the spanning key of each input coin. However, if the sender just generates these proofs, then others may steal these proofs and use them in other transactions. So we need to bind the proofs and the transaction. And our first attempt is to let the sender to sign the whole transaction use these spanning keys. However, if the transaction is signed as a whole, then it cannot be aggregated with other transactions to break the linkability, because others can figure out that there is an individual transaction. So we wanted to let the sender to sign an abstract of the transaction, and we found that the XIS is computed from the input commitments and output commitments. So we can regard the XIS as the abstract of the transaction. So we let the sender sign the XIS using this spanning keys. However, if in this way, others can find that these input coins belong to the same transaction. Finally, we split the XIS into n parts, where n is the number of input coins, and let the sender sign each part by using a spanning key. Then the sender, because the sender generates the transaction alone, and the receiver needs to obtain the private information such that the receiver can spend these output coins later. More specifically, the receiver needs to obtain the randomness and value and the spanning key. As for the spanning key, we directly use the stealth address such that the receiver can use the permanent secret key to recover the one-time spanning key. As for the randomness and value, we propose a new variant of L gamma. The ciphertext includes two parts, and the second part is the Peterson commitment, and the first part, and the receiver can use the first part and the description key to obtain the G2R and then obtain the randomness alpha. And given the commitment and the alpha, the receiver can obtain the H2V. And once the receiver the message space is small enough, the receiver can recover the value V from H2V. Okay, finally, let's see how to still spot the pass-through. In the original Mimblewimble, for example, we assume that E1 is the transaction one's excise, and E2 is the excise of transaction 2. And we assume that C1 hat is equal to C3. Then if the transaction 1 and the transaction 2 are aggregated into a big aggregate transaction, then the excise of the aggregate transaction is E1 times E2. Then the C1 hat and C3 can be cut. Then the output coins can be deleted from the aggregate transaction, so which is called cut-through. In our work, the excise is computed in the same way, so our scheme still supports the cut-through. Moreover, we define an ideal functionality for NIACS to capture its security. Unlike the original ledger, in our NIACS functionality, this functionality submits the aggregate transaction to the ledger, not the individual transaction. And our ideal functionality can capture the security properties proposed before, and also our ideal functionality can additionally capture the unlinkability because we define the coin ID. The coin ID is pseudo-random. So in an aggregate transaction, there are just some pseudo-random coin identifiers, which hide the values and the relevant parties. So others cannot figure out which coins belong to the same transaction. So which means the unlinkability. And we can use the ideal functionality to analyze the security of NIACS in complex execution environment, which is important in blockchain. That's all, thank you.
Okay, I guess we don't have a very inquisitive crowd today. So thanks again for the talk. And our next speaker is actually in person. Yeah, you're next, right? Oh, okay, sorry. Yeah, sorry, I thought you were third. Okay, indeed in person. So yeah, all good. Okay. Well, our next speaker is is Soren Thompson.
All right, so hi, my name is Søren Thompson, and I'm going to present the next work, which is Practical Provably Secure Flooding for Blockchains. This is joint work with Chenda Liu Zhang, Christian Matt, Uli Maurer, and Guillermo Rito. So to motivate this work, I would like to use blockchain as an example. And for the purpose of this talk, blockchain protocol is just a protocol where a group of parties interact in order to build a total order. However, such blockchain protocols does not guarantee this total order under all circumstances. It only guarantees that the order is built when each party owns some resource and a majority of these resources. And here you can think of resources as being either computing power or stake. And it only works when the majority of these resources actually behaves honestly. However, there's one often overlooked assumption for blockchain protocols. That is, they run on top of a flooding network. So for them to function correctly, we need both the majority of stake or resources assumption and that such flooding network actually exists. So let's have a look at what this flooding protocol actually is. So a flooding protocol, or in this case a delta flooding protocol, is a very simple protocol which ensures that any party is allowed to input a message and that this message will be spread out to all other parties within delta time. And this is what is assumed to prove the security of blockchains in a wide range of work. So such flooding networks are in practice implemented by a very simple procedure where each party, now for example P1, if P1 wishes to forward the message, he will select a subset of the parties as his neighbors, and then forward the message only to those parties. Then again, those parties will forward the message to a random chosen neighborhood, their choice, until all parties have received the message. This works all well and good as long as all parties remain honest. However, if a lot of the parties are corrupted, then either P1 has to send to a lot of parties, or otherwise there will be some parties that does not receive the message. Okay, so looking back to our blockchain example from before, this means that when we actually wish to realize such flooding network, then we need to rely on some assumption on the number of parties being honest. And that is, to build the total order, you will need to rely on both assumptions. Really would be better if you could just do with one assumption, namely the majority of honest resources. So in this work, we asked the question, can efficient flooding be realized assuming a constant fraction of honest resources or weight? And give an affirmative answer, yes, we can. In a bit more detail, our contributions are: we present a new flooding protocol called weighted fan-out flooding, and we will abbreviate this WFF. This is secure, assuming any constant fraction resources being honest. It has a logarithmic diameter for n parties, and it has a message complexity that is comparable to state of the art. Furthermore, we do extensive simulations of this new flooding protocol, which confirms that this in fact is practical. All right, so the model we use for our results is where we have a static set of parties, where each party is assigned some positive number of weight. Now, as before, an adversary is allowed to corrupt a subset of the parties, but the adversary will only, but our assumption is that the adversary is only able to corrupt corrupt parties such that a majority of the resources is left honest. And this phrase formally, right, there exists some gamma such that this fraction of resources owned by honest party is larger than the total fraction of total number of resources. And we note that this is implied by the standard proof of stake assumption. All right. So now let's try to develop a protocol that actually realizes flooding in this setting. So as a warm-up, we will do a very simple but inefficient protocol. And we will use the idea, well, how about take some existing flooding protocol and actually try to amend this to make parties behave proportionate to their weight. And as an existing flooding protocol, we chose the protocol by Matt Nelson and Thompson from 2022, where each party forward to the other party with a probability rho. As we know, this will ensure a logarithmic diameter for reasonable parameters, or a reasonable parameter rho. So we can depict this as this thing, right? So P1 forwards the message to P2 with probability rho. Now, to accommodate this to the weighted setting, what you could do is to let each party behave proportionally, meaning that P1 will instantiate 4 sub-parties, 1 for each discrete unit of weight P1 owns, and P2 will do the same thing. And now when P1 wishes to decide whether or not to forward a message to P2, what P1 can do is to let each party behave as a party in the existing protocol. So that is, each sub-party will flip a coin for each sub-party of P2. Now the total probability to forward will be 1 minus 1 minus rho to the power of the weight of the 2 parties multiplied together. However, this has a few unfortunate properties. So if we double the total amount of weight in the system, then this probability will increase by quite a bit. So what we intuitively want is that even though that we double the amount of weight, this probability shouldn't change. So our protocol should be invariant to scaling of weights. Okay, so let's try to develop this idea a bit. So instead of letting each party directly emulate a number of nodes proportional to their weight, what we'll do is to introduce a function which we'll call the emulation function to decide how many parties each node should emulate. So if this was the picture before, what we now have is that P1 will use this emulation function to decide how many nodes he should emulate, and he will forward only to flip a coin to forward for each of P2's emulated nodes as well. The total probability will be something like this. Okay, so let's think about what property we would like from such a emulation function if it should induce a practical protocol. So as we established before, we need that the emulation function should be invariant to scaling of weights. We want that all parties should emulate at least one node. And that is because we want each party to inherit the delivery guarantees from the original protocol. And then if you have a closer look of this Matt Nielsen-Thompson 2022 paper, then we note that the message complexity in the number of nodes. In this case, it will be in the number of emulated nodes. So we also want that the number of emulated nodes are low in order to keep the message complexity low. And then this message complexity is also linear in the fraction of honest weight. Sorry, in the inverse of the fraction of the honest weight. So we kind of want that fraction of honestly emulated nodes should also be high. Okay, so what candidates do we have? Well, we had a look at this, just assigning each party to emulate the number of weight they had before. This was, however, not invariant to scaling of weight. So to fix this, what we could do is to let each party emulate just a fraction of weight owned by a party P. So this is naturally invariant to scaling of weight. If you double the weight, the fraction remains the same. However, it doesn't fulfill the requirement that each party should emulate at least one node. So what could we do? Well, we could take the ceiling. It's still invariant to scaling of weight. And any party now emulates at least one node. Furthermore, the number of emulated nodes are reasonably low. In fact, this is just n. However, it fails to comply with the last requirement. The fraction of honestly emulated nodes are not high. In fact, this is similar to just let each party emulate one node. So it doesn't work either, right? Then we're back to the non-weighted setting. Okay, so as a final thing, try to take the ceiling of the fraction of stake owned by party P, now multiply this by the number of parties. So what do we get? Well, it's still invariant to scaling weight. All parties emulate at least one node. The number of nodes is reasonably low. This is less than 2n. But now the fraction of honestly emulated nodes are now less than, if gamma here is the fraction of honest weight, then the fraction of honestly emulated nodes will now be larger than or equal to gamma divided by 2. So this actually constitutes a fairly good protocol. However, there is a few issues remaining. First of all, to select the neighbors, well, P1 needs to flip a coin that comes out heads with this probability for each of his neighbors. This is kind of impractical, as we've heard before, that randomness is a scarce resource. Furthermore, it's not very practical that there's an unknown number of neighbors for each message. So in order to remedy this, we introduced this weighted fan-out flooding, which uses some of the same intuitions we had before. Again, we use an emulation function for each party. We use the same one which we just gained intuition for. Then we will let each party select a fixed number of neighbors. This will be some parameter of our protocol k times the number of nodes this party should emulate. Now, neighbors of a party are selected by weighted sampling without replacement, where each party again is weighted by the emulation. Let's just have a quick look at how this works. So if P1 wishes to send a message, well, then he will decide his neighborhood by first calculating how many nodes each party should emulate. So in this case, P1 emulates 2 nodes, P2 emulates 5 nodes, and so on and so forth. And now at random, let's just do it for lowercase k being equal to 1. Well, then P1 initially selects one node, one sub-node party at random, and then chooses to send the message to the party emulating this sub-party. Then the next one is selected by disregarding those, the nodes emulated by the party that already has been selected as a neighbor, and then selecting a new node at random. Then the final neighborhood will be just those parties. Okay, so the main result of our theorem, of our paper, is that if we set this parameter of the protocol k to be logarithmic in the number of neighbors plus some security parameter, and we divide by the fraction of weight, then we actually achieve a delta flooding protocol for a delivery time delta that is logarithmic in the number of parties. And this has a message complexity, which is just this lowercase k times n. And each party will have roughly k times this emulation function, number of emulated nodes as their neighbors. Okay, so in order to test the practicality of our protocol, what we did was to implement it, then among 1,000 nodes, simulate how often all parties had the message delivered for an increasing parameter lowercase k, and then counted how many neighbors each party on average had to choose. And this is what is depicted here. And additionally, we had an adversary that corrupted half of the weight, and the weight was assigned to an exponential distribution where each the heaviest party weighted a million times the weight of the lowest party. Then we varied the corruption strategy by the adversary to either be random corruptions, corrupt the heaviest parties first, or corrupt the light parties first. And what we see here is that independently of all these parameters, then if each party on average sends to roughly 45 parties, then the protocol succeeds with roughly 100% success rate. This number may seem, I don't know if it says anything to you, but what we could do is to compare this with existing protocols, which we will refer to as weight oblivious protocols. So we did the same experiment. We had an exponential distribution, which now had a parameter where the parameter refers to how the amount of time the heaviest party, the weight of the heaviest party is compared to the lightest party. And what we see that if we actually just have a constant distribution of weight corresponding to the non-weighted setting, well, then our protocol performs exactly equal to the original weight oblivious flooding protocol where each party simply sends to k neighbors. But as the weight distribution gets more and more skewed, well, then the success probability of the weight oblivious flooding protocol drops dramatically. However, our weighted fan-out flooding protocol remains secure for these 45 parties that are sent to on average. All right, so in conclusion, we present the first proof of the secure flooding protocol in the weighted setting and demonstrate its practicality using probabilistic simulations. And there are many more details and additional results. Among those are necessity of increasing neighborhood for heavy parties, necessity of logarithmic number neighborhood for fan-out flooding. Delivery, we show how to deliver the message to parties even with zero weight, and we do additional simulations. Thank you for your attention.
We're running ahead of schedule, so somebody should ask a question and get us back on track. Well, maybe I'll ask actually, like, how does, I mean, have you thought about kind of incentives and economic analysis of this and people potentially like manipulating their weight or reporting it truthfully.
Right. So you're right. This protocol depends on the weights being accurate, and therefore we kind of need to realize this somehow from an existing assumption. So I think that it's fairly easy to see how to do this from a proof of stake assumption, where all parties already know how many coins each party owns. But this is more difficult for, say, a proof of computational power, or proof of work, where you will have to estimate this in some reliable manner, as otherwise you will not guarantee security of the protocol.
Thanks. Okay, well, let's thank Soren again. Yeah, we'll move on to our last talk. Our last talk is snacks with Hamza Absallah, who hopefully is ready to share.
Do you see my screen?
Great. Yeah, if you're ready, Hamza, we can see your slides and hear you. So please go on.
Do you actually also see me? I don't see.
Yes, we see you and your slides.
Okay,
it looks great.
Okay, great. Okay, so welcome everybody to my talk about snacks. This work is jointly done with Georg Fox-Bauer, Peter Gaggi, and Karen Klein. I'll start off by talking about light client blockchain bootstrapping as a problem, and then define snacks, succinct and interactive arguments of chain knowledge, construct snacks generically from proofs of sequential work schemes, and then get back to bootstrapping and show you how to realize them generically from snacks. In light client blockchain protocols, you have full node provers that store the entirety of the blockchain, and you have light client verifiers that have minimal information about the blockchain, optimally the genesis block. The protocol, we would like it to satisfy a few properties. We would like the verifier to have sublinear effort, the communication to be sublinear, and the protocol non-interactive. If additionally the protocol achieves sublinear prover and no setup assumptions, that's a plus, and our protocol achieves all of these properties. So informally, in a bootstrapping protocol, the verifier depicted here on the right side, who has the genesis block B0 of the blockchain in question, potentially after reading a bunch of proofs from different provers, its goal is to output phi I, a commitment to the stable prefix of the blockchain. Why this is interesting? Well, this verifier can become a full miner itself if it wishes to. Okay, assume that it went asleep for some time and then now it catches up with the state of the blockchain and can continue mining. But additionally, assume that you have a bootstrapped verifier and say for different blockchains. So you have a proof of work Bitcoin blockchain and a proof of space Chia blockchain, and we have a bootstrapped verifier that has commitments to these blockchains. Then any prover can prove statements about, say, the transactions in the ith Bitcoin block and the jth Chia block by opening commitments to these blocks and then carrying out the proofs. So the idea of having a commitment to a blockchain is a very powerful tool. So this problem has a few solutions. So there's the generic snark solution, and there is the non-interactive proofs of work, NIPA-POS, and there's a fly client. Some limitations of these works exist. Some of them require setup assumptions. Some of them have limited applicability, say apply for proof of work blockchains, but say don't, or we don't know how to do them for proof of space blockchains. Some of them have limited usefulness, or even the notion of commitment doesn't come up in the construction. But more interestingly, for NIPA-POS and fly client, they work in a non-standard model where you assume that you're interacting with multiple provers, one of them is honest. If you are outside of this model, there are no provable guarantees. And that's a limitation. In this work, we define a classical proof system that underlies some light client blockchain applications, in particular bootstrapping. we construct snacks from graph labeling proof of sequential work schemes. And along the way, we give a new construction and generalize and unify existing ones. And we then show how these snacks as a tool can be used to realize bootstrapping. The advantage of this work is that you have a classical soundness guarantees, in the sense that if the verifier is reading a malicious proof, then it has a meaningful, measurable guarantees that I will talk about in a bit. This is in contrast to the NIPA power and fly client protocols. Our protocol is simple, generic, and modular, and it allows for exchange of ideas from the area of proof of sequential work schemes and light client blockchains. So in one slide, pictorially, how do we do this? So we assume that we start with a blockchain depicted here. It has the typical chain that you expect and few extra edges. And if we start with the graph of any graph labeling proof of sequential work scheme, here's an example, then what we show is that we build an augmented blockchain. We started from the chain on top, and we get the chain on the bottom, which is the union of these two graphs, essentially. And then we show how to build an augmented mining that labels the graph. So the mining for this talk will be generating the labels of the nodes of the graph. Then we define some witness relation, and then we define a proof system over this graph. And the proof system will be very similar to the underlying proof of sequential work proof system. So the idea is that we absorb the blockchain data into the computation of the proof of sequential work scheme, such that the sequentiality guarantees of the proof of sequential work scheme translate into sequentiality guarantees on the blockchain. So this is the main general idea. So with this slide in mind, let's dig into it. So before defining proofs of sequential work schemes, we need this notion of graph labeling. So you have a graph like this, and to label the graph, we generally use a hash function modeled as a random oracle, depicted here as tau. And the label of a vertex is the label of is the hash of the labels of its parents concatenated with its index. So for example, the label of 5 will be the hash of 5 concatenated with the labels of its parents, namely the label of 4 and the label of 1. Very standard notation. So graph labeling proof of sequential work schemes were introduced by Mahmoud et al. It's an interactive protocol between a prover and verifier, where completeness says that an honest prover that makes n sequential queries to its oracle makes the verifier accept with probability 1. Succinctness is what you expect. Proofs are Boolean logarithmic, and they can be verified in Boolean logarithmic time. The interesting property is soundness. Alpha epsilon soundness says even a massively parallel malicious prover that makes an alpha fraction sequential queries for alpha between 0 and 1, then it will make the verifier fail with a very large probability, 1 minus epsilon. So that says that parallelism does not help a malicious prover in convincing the verifier unless it actually did the sequential work that it was supposed to do. Okay, so this is kind of intuitively what the notion of sequentiality is. A simple proof of sequential work scheme that we give in this work, and it's a simple variation on existing scheme and on an existing scheme, is this, where the scheme is parameterized by a family of graphs that look like this, a skipless graph. The prover upon receiving chi from the verifier will use it to solve its hash function and build, and then here will be tau, and then compute the labels of the graph in topological order using this salted hash function, and then sends the label of the sink to the verifier, which will serve as a position binding commitment to the labels of the graph. And then these two parties run a challenge response phase for t many times. In each round, say here, for example, the verifier sends, okay, give me something related to the index 5. What the prover does in this particular proof of sequential work scheme is that it locates the shortest path that goes from the source to the sink and passing through the challenge 5 here, and then it gives the verifier the labels of this path and its parents. Okay, in particular, we say it opens this path, and the verifier will check the consistency of the labels of this path. And this path, although in this picture it looks like the prover is giving the entirety of the graph, it's actually still fully logarithmic. And notice that the shortest path is logarithmic, and the in degree of the graph is logarithmic. So all is good, but this is just a small example. Okay, so succinctness is achieved, and soundness is actually also achieved with. I would not bother reading the full theorem statement, but we'll highlight epsilon in the previous slide, the probability of failure. It depends on alpha and t, as expected, which is alpha to the power of t plus some negligible term that amounts to finding collisions in the hash function, the random oracle here, in q many queries in total. Okay, so this is a simple proof of sequential work scheme that I will carry on with me for the rest of the talk. So we're coming close to defining snacks and then materializing them. We need one more notion for that. We use the notion of weighted graphs, where a graph, say just an example like this, each node has a weight, and the sum of the weights of all the nodes is 1. Okay. And because we intended to absorb the blockchain data into the computation of the proof sequential work scheme, now the graph labeling, we need to adapt it a bit, and we absorb the blue data here, xi's, which will be blockchain data that I will show in a bit, into the computation of the label of the vertex in a very simple way. But now, the verifier in the previous slide, the proof sequential work scheme, was verifying the consistency of the opened path. But now we have an arbitrary data that we need to be able to verify its consistency. And, and we assume that this arbitrary blue data can be verified for validity by a relation arb-psi. Arb-psi is a relation that comes with a blockchain. Say you have the initial blockchain is a proof of work blockchain, and to verify the validity of the ith block or the ith label, you have a relation that tells you, okay, given the label of the ith block and the label of the parent blocks, you should be able to verify whether this block is valid or not. Say if it's a proof of work, you verify that the proof of work is valid. Okay, very simple. And with the notion of valid labels, you can define a valid path. A valid path, we call it alpha R valid if it's valid with respect to this relation R and it has weight alpha. Small details for the definition, and now we're ready to define snacks. And the way I'm building it up is that you see that a snack is essentially a generalization of a proof of sequential work scheme. It is as we define it non-interactively. So there's a proof bias and from the proof to the verifier, and we define it with respect to this witness relation, where the statement is a tuple phi n, where phi is a position binding commitment to a chain of length n, and the witness is an alpha R valid path in this graph, and an opening of the labels on this path with respect to the commitment phi. Okay, so this is our witness relation, and completeness says what is that an honest prover that has the labels of the entirety of the blockchain for alpha is equal to 1, the path is full weight, will manage to convince the verifier. Of course, you can think of it as the label blockchain or any graph. So the blockchain is just an example of it. Succinctness is what we expect. Soundness is also what we expect, but here we would like to define knowledge soundness. Alpha epsilon knowledge soundness is for every convincing prover, we can extract a path in this relation that is alpha R valid with very high probability 1 minus epsilon. Okay, so here I'm giving an example again. The blue thing is something that you can extract. And I would highlight the extractability guarantees are important because this witness relation is polynomial time relation. So ordinary soundness would be vacuous. We need to be able to extract from any convincing prover. Okay. So now coming back to the construction, so we started, remember, with a blockchain that was simple, and now we enriched it. We gave it this rich structure inherited from the proof of sequential work scheme. This is an example, and I wanted to show you how to do the labeling or the augmented mining. So assume you're a miner and you want to mine the fifth block, given the blockchain so far, and more important, the layers of the blockchain and the data, the transactions that you need to include in your block. So you want to compute G5 and H5. G will have two components, L, which will be a hash of the parents, and phi will be the commitment to the blockchain so far, including this hash. Okay, easy computation. And then you need to do what the original blockchain wanted you to do, generate a publicly verifiable proof. Say in a proof of work, you need to generate a proof of work that is valid. In a proof of space, you need to generate a proof of space that is valid, and so on. And this is by, and this is valid with respect to ARP psi. Once you have that, you have your label and you propose your new block. Okay. So I would like to say that in the efficient proof of sequential work schemes that you could potentially use to realize the snack, namely this construction that I show, or the CP construction, you have the LI, the hash of the parents, serve as the commitment. So you don't really need the extra commitment part. So this treatment is just generic, but in these particular schemes, you don't need an extra phi I. So the cost of this augmentation is an extra hash value in each block. If at the cost of this enrichment of the structure of the blockchain and an additional, say, 256 bits in each block, you will have a rich structure that allows you to build proofs of chain knowledge. So the prover and verifier, as said, they're almost identical to the underlying proof of sequential work scheme, prover and verifier, except for a small change that one has to be a bit careful with these extra edges that kind of become part of the proof of sequential work scheme graph, and they come from the blockchain. They may allow for shortcuts and to violate soundness, so one has to treat them carefully, and this can be done easily and simply. This is the only small change between the snack prover verifier system and its underlying proof of sequential work scheme. But this can be done. And what we prove is that if the underlying proof of sequential work scheme is alpha epsilon knowledge sound, then so is the snack. And this is not by accident, it's by design. And the security of our scheme is in the random oracle model. We apply the fiat shamir to the interactive proof of sequential work protocol. And anyway, the graph labeling proof of sequential work schemes are also in the random oracle, so there's no extra assumptions there. So this is the construction of the snack and how we augment the blockchain. And now we go back to essentially my last two slides about how to solve bootstrapping from this abstract object. So this object is interesting on its own, and you can potentially use it in other applications. Here is one motivating application that we wanted to use. So here's where we started. And now if you have, I'll show you how an honest prover generates a proof in the bootstrapping protocol. So here the honest guy is the green guy, the green bird. So what it does, it looks at, it has a blockchain of some length, n and I. It looks at the L suffix of the blockchain. L is a fixed number that I will talk about in a bit. And it sends these L blocks in the clear. This is SI. And for the rest of the blockchain, it generates a snack proof. Okay, so this is, you know, a blockchain that is labeled like I showed before, and you can generate a snack proof for it generically. And that will be the honest proof. And what does the verifier get from this proof? Completeness says if at least one of these provers is honest, then it will end up, the verifier will end up outputting a commitment to the honest L common prefix of the blockchain. And L is a number bigger than, a fixed number bigger than K, kappa, where kappa is the k-common prefix property of the underlying blockchain, which we assume that it's satisfied. How large is this L, and what kind of number is that? So this comes from an assumption that we make on the adversary and its computational power. This assumption was initially made by the Fly Client protocol. It's called the CL assumption. We refine it and adapt it to our work. And it essentially says that an adversary cannot create a fork of length L such that a C fraction of the fork is valid. So you can see if C is 1, for example, this collapses to the L common prefix violation assumption. But the generality of this, the range of the parameters for which this assumption holds is not really that well understood, and it will be interesting to analyze. But with this assumption and the guarantees that we get from the proof of sequential work scheme, we get to the crux of the soundness guarantees that we have here, which, as a promise, they are classical soundness guarantees, and their knowledge in terms of alpha epsilon knowledge soundness. What it says is that assume that all these provers that are controlled by a malicious prover that is respecting the CL assumption, then from any verifying proof, we can extract a path that is of weight alpha n here. And this alpha depends, I'm just showing the formula without needing to discussing it here. It depends on n, the length of the blockchain, depends on the C and L from the CL assumption. We can extract such a path except with probability epsilon. And of course, the closer alpha to 1, the better. You can, if somebody's claiming that they know the entirety of blockchain, then you can extract the entirety of the blockchain. But you can probably afford extracting 95% or whatever the number is that you need to plug in it here. And the larger alpha is, the stronger the CL assumption should become. So these guarantees are essentially almost best possible. They're extractability guarantees, except that alpha is not 1, but it's close to 1. And this is actually what allows us to have a much more efficient construction than snarks. The provers are sublinear; they do just lookup table. And finally, I would like to say that the guarantees of the SNAC system are extraction guarantees, correct? But what do they say? How meaningful they are in different blockchains? If the blockchain is moderately hard to mine, then these guarantees are meaningful. Say in a proof of work blockchain, we're generating a sequence of blocks, a long sequence of blocks that are computed sequentially and have valid proof of work is a heavy computation, and it's a heavy price to pay if you want to cheat a verifier. And this is so this is kind of has value and meaning. But if your blockchain is proof of stake, then it's not clear if the SNAC system that we develop, although it applies for it, the construction does not care about the underlying blockchain, what it is, as long as it has a witness relation that verifies validity in polynomial time. It applies, but the guarantees, I don't see that they have any meaningful guarantees for, say, proof of stake blockchain. So with this, I thank you very much, and I will be happy to take some questions. Thank you.
Okay, thanks a lot. And yeah, we have time for questions. Okay. Again, there's no questions from the floor. So that was our last speaker. So we will conclude there. The next session starts in about 10 minutes. So it's, I guess, not a full break. And if you, let's see, so if you stay here, there's a session on homomorphic encryption, and proofs and snarks is in the other ballroom. Thanks a lot.